Hello everyone, welcome back. So today's challenge is going to be Bangalore. So if you don't have any idea about memory permissions, then this video is for you. So as always, before we start solving the challenge, don't forget to try the challenge on your own. Try to just invest some time to solve it on your own before watching me or before we solve it together. And yes, don't forget to subscribe, don't forget to follow me on Twitter, and don't forget also to join the server, the Discord server. Yes, so let's not waste too much time and start the challenge. So what do we have? So overview, so this lock, so the lock uses the first MSP 430 ever to have memory protection. Okay, so he is having some memory protection. So this lock is attached to the lock ID Pro hardware security module 2. Okay, so what do we have? So as always, we try to start the program of the lock, and we have entered the password to continue. Remember, passwords are between 8 and 16 characters. So for example, I'm going to be sending 4141. Let's say uh, that's enough. So we have program is no longer running, and what we have, the password is not correct. Okay, so let's try to reverse engineer the code statically just to understand, for example, what this code is doing. We search for the main as always. Yeah, so this is the main function. So the main function is calling another function which is setup protection, and is calling a, let's say, a casual function that we have seen in a lot of macro corruption challenges, which is the login function. And then he's clearing the register 15. Okay, so this is interesting. So let's take a look, for example, at the login function, since it will be the first function that we have to investigate. So if we go, yes, so this is the login function. So what do we have? So he is adding this negative value to the stack pointer, which is just simply allocating some space for this stack frame of the login. And then he's moving 2400, which is the usual address that we have seen that contains, for example, messages or stuff like that. So if we go and investigate this address, we see that the 2400 should be having some kind of let's say message out there, or let's say some kind of pointer that points to a string, and that string is the message. So if we go to the log and functions, we see that we have this one here. If we reset and we set, so if we go and check 24, so enter the password to continue. So yes, so this is just simply a message, another, I suppose, message. And now we read the password. So before reading the password, so we are reading exactly, so we are reading so we are reading 0x 30 bytes of data. What else do we have? So we are reading those bytes back to the destination, which is the top of the stack, which is the stack pointer. Yes. And then we are moving 2465, which is this address, to the register 15. So basically this should be just another message. It should be another message. And then he is cleaning the stack, and then returning to return just to main. Yeah, so it is a basic thing that the login is doing. So for example, if we go and check that, we can just set another breakpoint at the return before, just after cleaning up the stack and before returning, just to check the return address. um, so what do we have? So if I'm going to be continuing again, so let's suppose I'm going to be given 4141. So this should be okay. Yeah. So what do we have? So if I'm going to be continuing so we do another continue, and what we have exactly. So yes, we are now at the return address. The return address is 4044, since it is inverted in the little Indian format. We just have to invert the byte. So the address that we will be returning to is 4440, which is 4440, which is this address, which is after the login exactly. So if we change this address to, for example, another, let's try to check, for example, if we have an unlock door function. There is no, is there any unlock door? So there is no unlock door. Is there any unlock door? Nope, there's only one function, that is the conditional unlock door that uses the hardware security module 2. Is there any interrupt, for example, so that we can craft something that can open up the door for us? Nope, there is no interrupt function too. So this is some kind of um, some kind of tricky challenge where we have, for example, we have to find a way on how we can, for example, unlock the door without using the functions that we have used in the previous challenge. So in the previous challenges, if you watch the videos, or if you remember that we have used, usually we use the unlock door function, um, we used the interrupt function too, and we used also another trick, which is trying to the conditional. If you go back to the unlock door function, um, unlock door function. So the conditional unlock door is basically not having any kind of interrupt to basically unlock the door. So it is not even going to be unlocking the door. So it is just going to be clearing the register 15 and then returning. So we have to find a way. On how we can unlock the door. So the idea is that what I did is just basically go into, for example, we can just go into another challenge. So let's say, for example, Johannesburg, and try to exactly know how the unlock door is happening exactly. So I wanted to know what is the code that the CPU was running in order to unlock the door. So to do that, I just had to go and investigate that on my own. So to do that, we can just try to debug a simple challenge that we have used, for example, Johannesburg, and see how exactly the unlock door mechanism is happening exactly. So to do that, we can just so I remember this challenge is just a simple buffer overflow where I have to just overflow a return address. So what do we have? What do we have? What do we have? What is the login? Yes. So this is the return. So if I'm going to be sending, for example, 41, let's say 41, 41, 41. So if we send that back, if we go and check the stack, we see that we have the C0, which is the stack canary. So we have to send 17 bytes of data plus the canary plus the return address. So if I'm going to be crafting something for that, so it's going to be 41 by 17 plus the stack canary, which is C0 plus the return address, which should be the unlock door function, which is 4644. Now if we send that, it should be unlocking the door as we have solved the challenge. So yes, it should be. So I'm going to be now investigating exactly how the unlock door is happening. So in the unlock door here, we will be pushing 0x7f as we have seen in a lot of micro-corruption challenges, and he will be calling the interrupt. Now the interesting thing, I want to know exactly how the interrupt is doing this, how it is unlocking the door. So he will be pushing the statute register, and then he will be moving register 14 into register 15, then he will be swapping the bytes, then moving that one, and then he will be just doing a simple OR um, with that value, and then he will be calling 0x10, which is the return basically. If we go back and see, so this is what the 0x10 is having. It's having a return. So before calling the return, he basically just passed down the statute register with this value. So the idea, guys, if we try to, for example, just craft something that do move um, move 0x ff00 inside of the statute register, and then just do a call to the 0x 10, then we will basically unlock the door. So if we assemble that, so if we try to send that, so once the CPU executes such a thing, he will simply unlock the door for us. So this is a simple code that can unlock the door without using any function that is defined by the manufacturer of the code or whoever wrote the code. Anyway, so this is the code that we can execute. Now, if we go back to the challenge that we have in our hand, we've seen that the login function is going to be cleaning the stack and then returning to the main. Now, if we go back and debug that a little, so we've seen that we have this return address. So the idea is pretty simple. We can just write the code that we want to execute and just make the login function return to the code that we want to execute. So this is a simple way to do that. We have done that, and I don't know exactly. I don't remember exactly the challenge that we have done that, but we've done that several times. So we just have simply to override the return address of the login and return to another place, which is going to be the code. So I can simply, for example, in here in our case, we have 16 bytes of data to overflow. Then we have to overflow the return address to the code that I will be writing also, which going to be, for example, in our case, in this place. And then I will be setting the address of that code to be 0040 or 4000, which is simply the address of the code that we will be writing to. So, so if we go on and use 41 by 17, for example, by 16, plus 0040 plus um, plus now the code that we have that's generated or that we have assembled. And just by using this code, let's try and see if we can get exactly what we want. So if we hit the return now, we are exactly at this address, which is 0040 exactly. So we will be jumping to this code. So we'll be returning to this place. Okay, so if we try to do that, so if we step back, so we are now at the code, so we are executing this code. Good. And the CPU saying it is invalid, and the program counter is at this address. So if we go and do one more step, we see that segmentation fault cannot execute write only page. So this is the interesting memory protection that is implemented in this code. So how can we break this? How can we bypass that? Now it is time to reverse engineer back the function that I have just skipped, which is this little function that we have seen that he was calling before calling the login, which is the setup protection function. So it is time to check this out. So if we go and see what this setup function is doing, so he is saving the register 11 in the stack, and then he's clearing up the register 15. Then he is calling the mark page executable. So he is marking some page as executable. We don't know exactly yet what this page is, and then he is also marking some pages as writable, and he is using some kind of, let's say, iterator or just counter, which is um the register 11 in our case. So this is going to be, so a register 11 is just a simple counter, and then he will be comparing this counter with the value 44, which is so if you go and check 44, so it is 68. And then each time he will be marking some page as writable. What else? So he then will be implementing the loop that we have seen, and then he will be also marking some other pages as executable. Okay, so this is a loop and this is a loop. That means he will be marking some kind of pages as writable and some kind of pages as executable. But those pages are actually spaces, or let's say memory spaces. So for example, this could be a page. This could be a page, for example. This, I don't know exactly how much data a page is having in this architecture, to be honest with you guys. But the only thing, I didn't dig deeper inside of this and that's inside of this paging mechanism. But to be honest with you, I just assumed that he will be marking some range of addresses as executable, and some range of addresses as writable, and some range of addresses as executable too. And the thing that I thought of just by trying to apply what I just assumed is that this address is going to be in the ranges of the pages that are writable and not the pages that are executable. So my idea was, since I cannot execute a page, which is this one. So for example, this code is living inside of a page that is not executable. The idea was, how can I make this page with this address, for example, um to a page that is executable. So I then started to think of a way of how I can now orient my exploit ideas into how I can exploit the paging thing. So this is where I just tried to, for example, thought of a way of how I can just mark how I can. The first thing that I thought, to be honest, is how I can just activate this mark page executable. The idea was, how can I call this function with the specific arguments that are there. So it's time just to investigate this more. So, and yes, I somehow landed on this function. So the basically stuff happens. So I go in a function, and that function was having some code, and the function is is also calling another function, and I had to investigate all of them. Well, I didn't investigate the mark page writable because it was not on the target. It was not on the targets that I was dealing with. So yes, so what do we have? So we have the mark page executable. So it was moving the register 15 to the register 14, and then it was pushing 0, and then push and then pushing register 14, and then it was subtracting 6 from the stack pointer and doing the kind of things with the stated register again. So my idea was, since if I can play with those two parameters, so let's try, for example, let's say for example I'm going to be calling this function. So I'm specifically going to be calling this function. So I'm going to be customizing these two parameters. So for example, I'm going to be passing the address that I want to make it executable, and then just ignite that call with using that address, which is 44BA. So for example, if I'm going to be customizing these two functions, so I'm going to be, since there is a call in here, so this is basically where the call happens. So I don't have to customize these two parameters, which is actually one parameter, which is the stated register, because it will always be subtracting 6 from the stack pointer. So I thought just of a way of how I can customize this too, and then just call this function, and by doing that I can mark my page as executable. And then there is an interesting thing I can do, is I can also change the return address of this mark page executable. And by doing that, so I can return back to the code that I will be marking as executable. So the idea is, the first thing that we have to do, so the first thing that we have to do, the first thing that we have to do is mark the page 40, what is the address? So it is 4400 as executable, as executable. The second thing is adjust the parameters for that page. And the third thing, change the return address of the mark page executable to the code that we want to execute, obviously. So those are the steps that we have to do. And yes, so those are the steps that we have to do. So to do them, we simply now have to go back to exactly the code that we have. So 41, 41, 41. If you go back a little, yes, so now we have this as the code. So we have to overflow with 16 bytes, then we have to change the return address to this address, which is this one, which is 44BA, and we will be customizing the parameters. How can we customize them? So just take a look at what I'm going to be doing. So we have 41 as a way to overflow. So just to make things more clear, just to make things more clear, I'm going to be using the minimum. Is there any way I can just a second, wait a second, I've got just an idea. um Anyway, what if we just have to overflow that? So to overflow that, we have to send 16 bytes of data, which are going to be used to overflow that one. And then the next thing that I will be doing is I will be setting the return address to the mark um, to the mark page executable, but I'm not going to be using 44b4 as the return address, because if I use that one, he will be executing all this code. But basically, I want him to execute this code, this code, this code, and so on. I want him to skip these two instructions because I'm going to be customizing those parameters for the mark page executable function. So to do that, so basically, how can we customize them? Now, this is the question. So we've done that several times too. So to do that, we have to push them into the stack as a way just after calling the function. So I'm gonna be assuming that the function is called. So the thing is that we know that before calling any kind of function, we have to pass down the parameters, and the parameters should be before the calling of that function. So if I just try to so the calling of the function is going to be at this address, which is 44BA. So since it is a little Indian, we have to flip the bytes, and then now I'm going to be passing the parameters that I want exactly to execute. So let's say, for example, I'm going to be so basically now we are going to be executing this instruction, and we are going to be marking a page as executable. So the parameters are going to be the address of the page that I want to make executables, which in our case I'm going to be making the 400 page as executable. Um, and then I'm also going to be passing that 0, since we have a push 0 also. So I'm going to be calling that with a 0. And then we have to adjust the return address exactly to where we are going to be returning next. So it's a kind of it's a kind of chain, yes. So this is the first return. So I'm going to be returning to this code, and then let's say I'm trying to do some kind of oriented programming, or let's say return oriented programming, or ROP or ROP or whatever. I didn't make a video on that, but it's just trying to just trying to do that. Anyway, so after we do that, so we are now fully in the code. So we have passed down the address where we want to make this page executable, and this is just passing the parameters the same as it is, as the one he is just doing. I'm just mimicking what he's doing, and the other one, and for the resistor 14, I'm changing that manually or just customizing that. What else? So basically, after doing that, so the code, if we try to make that, so this is E2 and E2 bytes, so this is the 4 bytes. So this is the return, and this is 4 bytes. This is now should be the return address, and this is where our code will be living. So the address of the code should be 40 plus 6, which is 14, which is 14 and 6. It should be like that, but since it is in Little Indian, it should be inverted too. The byte should be inverted. So what do we have now? Next is going to be the code that we have drafted, which is this one. And yes, this should be our payload. So let's try to see what this payload is going to be doing. So if we reset and we send this code, so we have that we have overflowed the buffer of the password, and now we are overriding the return address to be BA44, which is going to be executing exactly inside of the mark page executable function. And then we have customized the parameters to be like, I'm saying that I want to make this address or this, let's say, page um to executable. Just one thing to say, guys, is that a page is basically having some range of addresses to be holding, and I don't know exactly how much addresses a page is holding, because simply I don't know how this architecture is working with the paging. I didn't dig deeper with the paging thing for the MSP 430, but what I'm just assuming that this address is going to be in the ranges of writable, because this is how he set the protection for the memory, and I'm trying to just pass down this address to the mark page executable to make it executable, obviously. And I don't know exactly how much bytes I'm going to make executable, or what is the range of addresses that I'm going to be making executable out of this address. But what I'm pretty sure about is that those 16 bytes are having the permission to be executed. So this code is having obviously the permission to be executed. This is what I'm pretty sure about. And so yes, we have just passed down those parameters, and then I'm executing that. So I'm going to be using steps to step in the code and see what I'm going to be executing. So we are now in the mark page executable. We go into that. So we are calling the return. We are executing, and somehow now we are in the call. We are in the call tan. So once we are in the call tan, and this say, well, we have another segmentation fault, cannot write to execute only page. So we are now having another problem, which is that this address is not writable, which means we cannot write to it. Now this is a problem. Why? Simply because we cannot go into that one. Now the idea in here was simply to make to solve this issue. I just had to, since the call is basically just doing a jump to the 10 and then returning back, so I want just to execute this return function. So to do that, I just had to, let's say for example, I'm going to be moving directly this 0x10, directly inside of the program counter. Instead of doing a call to the 0x10, we can just simply do a 10 to the, we can just move on 10 to or 16 to the program counter directly, which is basically the address of the program counter. And the issue because of this segmentation fault is that we cannot write to execute only page. Is that, for example, I think now, I'm just assuming, guys, I'm not sure yet, but I think the page is holding this offset of address. So if I'm going to be trying to override, let's say for example, since the call is going to be pushing the return address, so I think I cannot push the return address in this place. So that's why the call is going to be pushing something inside of the stack, and I don't have the permission to write on that. One. I don't know exactly yet, but I'm just assuming again. I basically solved this challenge just by assuming a lot of things. Yes. So I think now we can just simply skip the calling function by passing down directly 10 to the program counter, and by assembling that and by changing that, um, we can just now try to use this code and see what we are going to be having. So I'm going to be continuing, and yes, the door is unlocked. So this is a way on how we can just exploit it, this one, guys. So it's a really interesting one. I hope you learned something new, and see you in the next video. Bye.